Welcome back to your Cisco Cert Success Path. In our previous video, we took a look at your IT career success blueprint with those foundational skills and practices and habits that will help us build a strong foundation for our career. Now, here in stage one, or phase one as we call it, we're going to be getting into some of our technical studies, Network Plus. We'll take a look in this video at some of the technical topics on the Network Plus exam. And as always, throughout these videos, I want to give you a big discount on furthering your training as you go into Network Plus, because I've created a complete video course for Pearson IT certification covering every topic on the blueprint for the new Network Plus exam. That's the N10-007 exam, the 007 exam. But here in this video, I just want to give you a sense for what the Network Plus content is like, and we'll teach a little bit of technical content along the way so you get a sense for what you're getting into. But let's get going right now by just taking a look at some of the broad topics on this exam. One of the big ones is protocols and reference models, like the OSI model or the DoD or the TCP/IP model, things like that. We should know what port numbers are used by various protocols. You need to know about different types of network devices, everything from the basics like routers and switches to some higher-end firewall and security appliances. Also, you need to be able to distinguish between different network topologies and categories such as a WAN or a LAN or a MAN or a PAN or a CAN. Those are some of the different categories. And for the topologies, you need to distinguish between things like a bus, a star, a full mesh, a hybrid, things like that. You also need to know about various network services that are out there, different WAN technologies like MPLS is one example. We'll take a look in this video at some of the different cables. You need to know about the connectors as well used by those different cables. Ethernet switches, that's a big topic, as well as wireless networks. We'll consider wireless networks a bit in this training. And a huge topic is network addressing, knowing how IP version 4 addressing works, knowing how to do subnetting, and also knowing how IP version 6 addressing works. And it's based on those addresses that our routers can make forwarding decisions based on those layer 3 network addresses. And in the full course, there's an entire module just on routing where we get into different routing protocols and exactly how does routing work in theory. You also need to know a bit about unified communications. This is where we're not just sending data over a network, we're sending maybe voice, data, and video. It's a unified network, and we're communicating using all those different types of media. Virtualization is a major trend that's sweeping the IT industry these days. But here we're talking not just about virtualizing servers using something like VMware, but also virtualizing network devices like routers, virtualizing switches, virtualizing network interface cards. Security is an ever-increasingly important topic, it seems, and there's an entire module just on network security in the final course, as well as network monitoring and management, some network best practices, as well as troubleshooting. We'll consider troubleshooting a bit as well. And by the way, not listed here because it's not a technical topic, but in that complete course that I told you about, and I'm going to be giving you a discount on a little bit later, in that complete course, we have a final module which gets you ready to take the exam. It tells you how to plan out your study schedule, how to get your hands dirty, as I call it, how to get some practice on some gear, and how to psychologically prepare yourself to calm your nerves and help you to excel on the exam. Now let's dive into just a sampler platter, if you will, of some of the different technical topics that we're going to be covering in the Network Plus curriculum, starting off with protocols and reference models. Some things just have to be memorized, and this is one of those things. We need to memorize a couple of tables full of protocols, understand what those protocols do, and know what port number they're using. For example, Telnet, we need to know that that uses TCP port 23, and we would need to know what Telnet is, and maybe why we should not use it because it's unsecure communication. We should probably use Secure Shell instead. Here's yet another slide full of content that we need to memorize for the exam. We also talk about the OSI model, the 7 layers. A lot of people get confused. We'll not go into all the layers in this short training video, but a lot of people get confused about which layer is at the top and which layer is at the bottom. Some people think that the layers start at the top with layer 1 and work down, but I compare it to a building. If you think of a big skyscraper building, where is floor 1? It's on the bottom. It's the same thing with the OSI model. Layer 1 is on the bottom, and then we build on top of that with layer 2. By the way, layer 1, that's where the bits are sent back and forth. Electrical signals on copper wire, photons on fiber optic cable. At layer 2, that's where the Ethernet switches live. At layer 3, that's where the routers live. At layer 4, that's where we have protocols like TCP and UDP. We're setting up and maintaining and tearing down sessions at layer 5. Here we might have a protocol like SIP, the Session Initiation Protocol. Layer 6 is how we're formatting our data. Are we using ASCII or EBCDIC or one of the many different types of formats out there? Layer 7 is the application layer. This is where the user is interfacing with the network. They're using some sort of an application, maybe like an email server's application. And in the final course, we talk more about each of these layers. One of the technical topics we need to know is the MTU, the maximum transmission unit. The MTU is the largest frame size or packet size. Frame is a layer 2 entity and packet is a layer 3 entity, but we can say MTU and then specify, oh, I'm talking about a layer 2 MTU or I'm talking about a layer 3 MTU. But typically we talk about layer 3 MTUs, the size of a packet. And let's say on this router we've got an MTU of 1500 bytes, which is typical. That's what we commonly see as a default setting. If we have a frame going out that same interface, its MTU might be 1518 bytes because the layer 2 header that gets added on to the layer 3 packet to make it a frame. With Ethernet, that's an 18-byte header. And if everything matches up at the far side, we're good to go. We can exchange packets and frames and there's no problem. However, we can get into a bit of an issue if we have a mismatched MTU. Here, the router has an MTU packet size of 1492 bytes. Let's say that the switch tries to send a 1500 byte packet into that. Well, it's too big. So what's going to happen? Well, the router can try to fragment it, cuts it up, and then it can send those fragments individually. But sometimes we might send a frame that has the DF bit or the don't fragment bit set, and that would prevent a packet from being fragmented, at which point it would be discarded. When that happens, router R1 is going to let the switch know. It's going to send an ICMP message back that says fragmentation needed and DF set. And this was with IP version 4 specifically. With IP version 6, there isn't a DF bit, but there is a packet too big ICMP version 6 message. Let's take a look at some network devices. One thing we need to understand is how CSMA CD works on a bus topology when we've got printers and servers and PCs attached to this bus topology. This is the way it used to be when I started working with networks back in the late 1980s. We had a coaxial cable weaving from room to room throughout an office building, and PCs would tap into that coaxial cable. And the way that a PC would transmit is it would listen to see if the coast was clear. And if it did not hear any other traffic on the network, because there can only be one packet on a segment at any one time, if it didn't hear anybody else, it would assume, hey, we're all good to transmit, and it would transmit. However, here's what could happen. If two PCs were listening to the same period of silence, they could simultaneously and incorrectly conclude that it was safe to transmit. They both transmit at the same time, and boom, we have what's called a collision. And if that happens, then these PCs that had the collision occur, they're going to be able to detect that. A hub can send a jamming signal to tell the PCs that bad stuff just happened on the network, or it might detect a voltage spike on the network to realize a collision happened. And each of those PCs are going to set a random back-off timer. Now, hopefully those are going to be different random numbers, and they'll wait for those timers to expire before they send again. And then, hopefully, there will not be a collision if they have different timer settings. This is something called CSMA CD, Carrier Sense Multiple Access with Collision Detection. Carrier Sense means that we can sense that we're on the network. We know that we're able to transmit, and it's a multiple access medium, meaning that multiple PCs can tap into the same network segment, and we're able to detect a collision if a collision occurs. That's a little bit different than CSMA CA. That's Carrier Sense Multiple Access with Collision Avoidance. We see that oftentimes in wireless networks. Here, again, the wireless clients, they listen to the air this time. They listen on their radio to see if the coast is clear. And if client 1 transmits into the wireless access point and client 2 transmits into the wireless access point, and they do so at different times, everything is great. But this is a shared medium, much like that bus topology. So if client 1 is transmitting, client 2 hopefully will hear that transmission and it will realize, uh-oh, somebody's transmitting. I'm going to be quiet until the transmission dies down. Then I will send out my signal. And in that case, the client can set a random back-off timer and it can try again. But we could run into an issue where the client is sending a signal that's heard by the wireless access point, but it degrades, it attenuates, it fades out before it gets to the other client, just as you saw on screen. That's something called the hidden node problem. There, client 2 might listen to the radio, listen to the air to see if anybody else is transmitting. Doesn't hear anybody, it thinks it's clear to send, and it sends, and yeah, we have a collision. That can happen if our clients are fairly far apart, even though they might individually be able to reach the wireless access point. Some of the other appliances that we need to understand for the exam include a next generation firewall or a layer 7 firewall. This is going to be able to understand the nature of an application. It knows that when I send out a SIP message, for example, I might be setting up a video call or a voice call. So it's not surprised if it sees the real-time transport protocol is just an example. You don't have to memorize that. But it understands what protocol comes after SIP. It can also do deep packet inspection. It can even determine statistically that an encrypted packet is malicious. Can you imagine that? Having malware encrypted seems like a way to prevent detection of that malware. But through the examination of large data sets, these next generation firewalls, they can statistically determine and look at some of the clues to determine with over 99% accuracy that an encrypted packet is malicious. We could also have intrusion prevention built into this next generation firewall where if malicious traffic is detected, we can drop it. We can stop it in its tracks, as well as maybe setting up some sort of access control to prevent any more communication coming in from an offending host on the internet that's sending us this malicious traffic. Another filtering appliance is a content filter. This might be used in a home by parents. They don't want their kids to watch something that they consider to be objectionable. Well, they could install some software on their PC to filter out that type of content. Or in a large enterprise, there might be an appliance dedicated to content filtering specific types of content. Another appliance is a UTM, a Unified Threat Management appliance. This is kind of the best of all worlds. It groups a lot of different features into one appliance, such as it can be simultaneously a firewall, an intrusion prevention system sensor. It can detect and filter out malware. It can be a VPN termination point. It's a virtual private network. All that within one appliance. There's also a series of network services that we need to know for the exam. Let's take a look at one of them here in this video, DHCP, the Dynamic Host Configuration Protocol. We should be familiar with this one because most of our devices, when they boot up, like a phone getting on a wireless network or a PC or a laptop booting up on a network, typically they're going to use DHCP to determine their IP address from a DHCP server. And not just an IP address, that DHCP server is also going to tell the device, here's your default gateway, here's your subnet mask, here's your DNS server that you can go to resolve a domain name to an IP address. Now in this example, laptop A is just coming on the network and it desperately wants to get some IP address information. The way I want you to remember this exchange between a client and the DHCP server is to use the acronym of DORA, D-O-R-A. When my two daughters were small, they used to watch Dora the Explorer. You might remember that show from way back. That's what I think of whenever I think of DHCP, because DORA, D-O-R-A, that represents the four-step exchange process that we go through to get an IP address. The D in DORA reminds me of the D in the Discover broadcast message that gets sent out. You see laptop A sent out a Discover message to the DHCP server, but did you notice what happened when it hit the router? It was a broadcast, and routers don't typically forward broadcasts, so the router dropped that packet. Okay, not a problem so far because laptop A is on the same subnet that the DHCP server is. And the server responds with the O in DORA, which is the offer message, saying, yes, I'm a DHCP server. I would be happy to serve your IP address needs. And whoever responds first, because there could be more than one DHCP server on the network, laptop A is going to select the first one that responds and then send the R in DORA, a request message, directly to that IP address that responded with an offer and say, yes, can you please give me IP address information, which will cause the DHCP server to then respond with the A in DORA, an acknowledgement message saying, yes, here's your IP address, your subnet mask, your default gateway, your DNS server, and perhaps lots of other information. But one of the challenges we have is what happens when laptop B wants to get an IP address, because it's not on the same subnet as the DHCP server. It has to go through a router. How is it going to do that? Because after all, when it sends out its Discover broadcast, that's going to get discarded because a router doesn't forward broadcasts. A router separates broadcast domains. Well, what we need to do is to configure that router as a DHCP relay agent, also known as an IP helper. Once we do that, the router then has the ability to forward specific types of broadcasts, including DHCP. There's like 9 different types, including DHCP. It can forward that broadcast over to the DHCP server. So just like before, laptop B is going to send out a broadcast, and that's going to be responded to by the DHCP server with an offer, and it's going to say, yes, I would like you to provide me IP address information, which the server does, and now laptop B, it has IP address information because we configure that router as a DHCP relay agent. Next up, let's consider some DHCP features that we might have. You need to know some of the details about DHCP. You might have certain reservations that you want to make. Every time a certain device boots up on the network, you want it to have the same IP address. Maybe it's a file server. Maybe you're sharing files from it. Maybe it's a print server. You always want to be able to go to this one IP address and know that it's the print server or it's the file server or some other network of service. What we can do is associate a device's MAC address with an IP address. We can make a MAC address reservation. So the AAAA and BBBB, CCCC, 1234, that could always be mapped to an IP address of 192.168.1.125. Or we could have pools of addresses. In fact, we could have a combination of both. A pool, also known as a scope, that's typically a subnet containing a pool, a grouping of IP addresses, and we could have different pools for different subnets. So different PCs and different subnets, they could still use the same DHCP server and be assigned an IP address in their appropriate subnet. Now, some IP addresses we do not want to hand out. It might be the IP address of a printer or a router or something else. What we can do is exclude certain IP addresses so we don't hand those out. And we can have in our scope options that we hand out, such as a default gateway, a DNS server, time to live values. Option 150 is another option. That's a TFTP server's IP address. That's oftentimes used by a device on the network, like an IP phone as an example, where the IP phone can boot up, it can learn its IP address information and the IP address of a TFTP server, and it can reach out to that TFTP server and download its configuration from that TFTP server. The IP address that the DHCP server assigns has a certain lifetime. It's called a lease time, and we don't wait until the lease time, which maybe is 3 days, this one example. We don't wait till the lease time runs out and say, uh-oh, we need a new lease. Now, what we do instead is at 50% of the lease time, 1/2 the lease time, we send out, as a client, another request to the DHCP server that says, hey, you remember you assigned me this IP address? I'm halfway through my lease now, and I'm going to need to continue using it, so can you please renew my lease for another term, whatever that lease time is? And if the DHCP server is up and available and willing to do so, great. If it doesn't respond, because maybe it's down, maybe it's unreachable, who knows, but if it doesn't respond, we're going to try again at the 7/8 mark, which I think is like 87.5% of the lease time, and hopefully we'll get our lease renewed then. If it doesn't renew then we'll try again after our lease completely expires. Let's take a look now at some different cabling that we might have in our network. We have copper cables and fiber optic cables oftentimes. Here, we're taking a look at different types of copper cables. Coaxial cable might be used in a cable modem. You might have this cable TV cable coming into your home. We used to use coaxial cable a lot in early local area networks like 10base2 and 10base5. Don't see that much anymore. Instead, we probably are going to be using a twisted pair cable. You see, one thing we're trying to prevent with either of these types of cable is we're trying to prevent EMI, electromagnetic interference. We don't want radio waves to come into one of these wires and corrupt the signal being transmitted over the wires. Also, we don't want those wires to become antennas and start transmitting their own signals and interfering with other things. So with the coaxial cable, we have that sort of a mesh of wire that's surrounding an insulator, that's surrounding an inner conductor. So that outer mesh of wire, that's providing the insulation from EMI. With twisted pair cable, tightly twisting pairs of wires, that allows the wires to protect one another from EMI. What we're doing is twisting the wires where the length between the twists are less than 1/4 of the minimum wavelength being transmitted over that wire, and that way the wires are protecting one another from EMI. Another term we need to know is impedance. And impedance is really a combination of resistance, capacitance, and inductance, but impedance can degrade an electrical signal over a distance. And because of this impedance, there are some distance limitations that we have on copper that we don't necessarily have on fiber. Now, what types of coaxial cable are out there? Well, RG59 and RG6, those are commonly seen in home installations. They have a 75 ohm impedance. RG58, that was commonly used sort of in the old days with 10 base 2 networks. We don't see that much anymore. And twisted pair cable, we can have unshielded twisted pair where we don't have any additional shielding. The wires are just wrapped around one another tightly. Or we're starting to see shielded twisted pair coming back for some of our really high end speeds, like 10 gigabits per second. We could have STP where we start wrapping those pairs of wires with additional coating, like an aluminum jacket could go around a pair of wires. And if we're running a twisted pair cable through a raised floor or drop ceiling or an area that's going to be acting as an air return duct, then we might want to use plenum rated cabling, or if we're sending air through that duct. Because think of what could happen if there's a fire in the building. The cable jacket, if it catches fire or if it has a lot of heat that it's exposed to, it could start to emit fumes. And if those fumes are emitted in part of your HVAC system, can you imagine you're pumping toxic fumes throughout the building? That's bad news. So what you want to do in those types of areas, in plenum areas as they're called, you want to use plenum rated cable where that doesn't happen if the cable catches fire or if it's exposed to extreme heat. We also need to understand some of the different distance limitations for different categories of twisted pair cable. For example, back in the old days when we had private branch exchange PBX systems, those were telephone systems that businesses installed, they oftentimes used Category 3 wiring, and then when local area networks started coming along, people realized, hey, we can use this Category 3 wiring and run network signals over this wiring. And that was fine for 10 megabit per second or 10 base T networks. And there was a way to use all 8 wires in a Category 3 cable, and you could even squeeze out 100 megabits per second. That wasn't done very much, though. Typically, Category 3 was just serving 10 base T clients. And you could go for 100 meters over a Category 3 cable. Then Category 5 came along, and that let us use just a couple of pairs, in other words, 4 wires in this 8-wire cable to do 100 base TX. We used pins 1, 2, 3, and 6 out of the 8 pins, and that could go for 100 meters and transmit data at a rate of 100 megabits per second. The main difference between Category 3 and Category 5, well, Category 5 might have had a different gauge of wire, a thicker wire, but also it was twisted more tightly. We could even run 1000 base T over Category 5. If we do that, though, we're using all 8 wires, not just a couple of pairs of wires. Category 5E improved some of the specs on Category 5. Still, though, it could transmit 100 base TX or fast Ethernet, or it could transmit at a gig rate. Category 6 ups the game a little bit. Not only can we travel at a gig rate over 100 meters, we could travel at 10 gigabits per second, but the distance limitation drops down dramatically if we go for 10 gig. If we go for 10 gig, we're limited to 55 meters. If we don't want that limitation and we're going to be using a lot of 10 gig in our network, we might want to use Category 6A. That will get us 1 gig or 10 gig for 100 meters. And more recently, there's been Category 7 that's come out. This will get us 10 gigabits per second over 100 meters, or we could do simultaneous POTS, which is telephone service, CATV, which is cable TV, and 1 gig for data. So voice, video, and data could simultaneously be flowing over this Category 7 cable over a 100 meter distance. Now, these twisted pair cables, they typically terminate with a connector called an RJ45 connector. And the color of wires that we assign to different pins in those connectors, that's determined by what's called an IATIA standard. And one of the common ones you'll see out there today is IATIA 568B. And that's what I'm illustrating for you here on screen. But let's take a look at some different types of cabling and how these pins on one side connect to pins on the other side of a cable. If we have something like a PC, that's called a media-dependent interface. And if it connects into an Ethernet switch, that switch is called an MDIX, a media-dependent interface crossover. In other words, the transmit pins on the PC side, they connect to the receive pins on the switch side. Because think about it, you wouldn't want transmit connecting to transmit. No, transmit needs to transmit into a pair of wires that are receiving. And the receiving wires need to connect into a pair of wires that are transmitting to it. So this works great for something like 10 base T or 100 base TX. Notice we're only using a couple of pair. We're using pins 1, 2, 3, and 6. The other pins are unused. If we're trying to connect a couple of PCs together, though, that could be a problem. Here we need to use a crossover cable, which causes the transmit leads on one side of the cable to be connected to the receive leads on the other side of the cable. For 1 gig connections, we need to use all 8 wires, so not just 2 pair anymore, we're using 4 pair. And here we see what a straight-through cable looks like if we're connecting a PC into a switch. But if we need to do a crossover between a couple of PCs, just as your reference, here's how that would look. We also have different transceivers that we can install in Ethernet switches that might be a way to have a fast interconnection going into that switch. And for a long time, there's been something called a GBIC, a gigabit interface converter that runs at a gigabit per second. But there are many faster options out there today. I remember using GBICs back probably nearly 2 decades ago. Now we might see something like a small form factor pluggable or an SFP transceiver. An SFP transceiver also runs at a gig, but you can see it takes up a lot less real estate. It's much smaller. We could have an SFP plus, which runs at 10 gigabits per second. Or we could have a transceiver called a quad SFP or a QSFP. That gives us 4 times the speed of the SFP. So 4 gigabits per second. Well, the one I'm showing you on screen is actually a quad SFP plus. He gives us 4 times 10 gig. So this one connector, it's got a 40 gigabit per second throughput, if you can imagine. And the way fiber worked for many years was we had a transmit fiber and a receive fiber, and this was called a full duplex connection. We transmitted with one lead and we received on another lead of fiber optic cable. But now there's something called a BiDi transceiver. With a BiDi transceiver, we use wavelength division multiplexing, one wavelength for transmission, one wavelength for reception, and we're able to both simultaneously transmit and receive over the same fiber optic strand, just by using different wavelengths of the laser light. Something else Network Plus wants us to know about is the different types of tools we would use when we're troubleshooting or working on a network. Let's take a look at a few of those. We talked about how the RJ45 connector would go on the end of a twisted pair cable. We would make that happen with a crimper. We put in an empty RJ45 connector and we feed the wires in there, matching that IATIA color code that we're using, and we would squeeze really tightly and it would put the end on a cable for us. Sometimes we're not sure if we're dealing with a crossover cable or a straight-through cable, or maybe in building wiring there might be a cable that's broken. What we could use is a cable tester. You put one of these devices on each end of a cable and it will show you how a pin on one side connects to a pin on the other side, or maybe doesn't if we have a broken wire in the middle. If we're putting a wire into a wiring block, like a 110 block they're called, you might use a punch-down tool to make this wire be inserted between 2 little metal blades. And these blades, they cut into the wire just deep enough to make contact. They cut through the insulation and make contact with the inner conductor. And if we're troubleshooting fiber optic cabling, it's really handy to have something called an optical time domain reflectometer, or an OTDR. I used to use one of these where we could put a fiber optic cable on it and it could send out a certain wavelength of light. And if there was a break in the cable somewhere, that break would cause some of the light to be reflected back to this OTDR. And by knowing the speed of light, given the particular type of fiber we were using, This OTDR could calculate with really good accuracy where that break occurred. So if you need to go dig up something, maybe a backhoe dug into your conduit and broke a fiber, well, this could give you an idea of exactly where you need to be digging. You could also test a copper cable for errors. You could do a bit error rate tester where you could see your rate of errors that are being received. You could check the strength of a fiber optic source with a light meter. Something else you could do is use a tone generator if you're working with a bunch of wires coming into maybe a wiring closet and you're not really quite sure where they go. Well, what you could do is use what's called a fox and hound or a tone generator. You generate a tone on one end and then you take what's called the hound in this graphic and you can go to where you think the cable should be coming out and you can just hold this little hound close to the cable. And if it's the right cable, it's going to start making a noise. You'll be able to audibly hear it on a speaker. And that's a way to identify cables in one room connecting to cables in another part of the building. We also could have a loopback adapter that CompTIA wants us to know about for the Network Plus exam. A loopback adapter can be plugged into an RJ45 connector, maybe in a switch or a router or a PC, and it loops the transmit leads back to the receive leads. That lets us test if we're able to actually send traffic out and receive traffic on a network interface card. Something that is super handy to have in the real world is a multimeter, like a digital multimeter, which could measure things like voltage and resistance and amperage. And something that's a software tool rather than a hardware tool is a bandwidth speed tester. There are several of these out on the internet. My personal favorite is to go to speedtest.net and you can do a speed test to see what your upload and download speeds are for a connection, as well as the round trip delay. That's your ping time. We could also have a spectrum analyzer to see exactly what is the amplitude or the signal strength of different light waves that are crossing a fiber optic cable. And just as a composite list, here are some of the different cabling tools that we need to know for the Network Plus exam. Next, let's consider some of the characteristics of wireless networks. We could have an infrastructure wireless LAN. Maybe you have this in your home where you have a wireless access point, or you might have an ad hoc wireless LAN where you don't really have an access point. You just have one wireless device connecting directly to another wireless device. Something getting a lot of popularity these days is to have a mesh wireless LAN. This is where your access points don't have to be cabled into your infrastructure. You could just have an access point sitting outside, for example, and as long as it receives a strong enough signal from an access point maybe on the inside of your building, it can receive that signal and regenerate it. So you can have access points scattered geographically around an area without those physically being cabled together. We also need to know about the different bands of wireless frequencies that are used. The 2.4 gigahertz band and the 5 gigahertz band. Typically, the 2.4 gigahertz band is a lot more crowded with things like microwaves and baby monitors, and there's just not as many frequencies available to use here. You can see that if we do use the 2.4 gigahertz bands, in the US, we should select only channels 1, 6, and 11. Because if I select channel 1 and then think, well, I'll select channel 2 for my next access point, those don't overlap. Just because we say we're using channel 1, that doesn't mean we're only sending on that one frequency. You see there's sort of a Gaussian drop-off there where we're spanning nearly 5 channels. So to get 5 channels of separation, we need to go with channels 1, 6, and 11. That's in the US. Outside of the US, you could also use channel 14. But you could group different cells of these access points together where they have non-overlapping channels, where they're not interfering with one another. Looks sort of like a honeycomb, as I have drawn on screen. Something else to just memorize, another table to memorize, would be the different wireless standards, the different IEEE 802.11 standards. And we give you a table like this in that course to memorize. And the last technical topic we get into in the course is network troubleshooting. And CompTIA gives us a 7-step troubleshooting methodology, beginning with clearly identifying the problem. We want to gather information surrounding that problem, and if possible, we'd like to be able to duplicate it. It's hard to fix something if we cannot duplicate what happened. We might need to interrogate the users to say, when did this start? Does it happen all the time? Is it worse during certain times of the day? We gather that type of information. We identify the specific symptoms. Like if they say the internet is broken, you know what? The internet is probably not broken. Maybe they just cannot go to one website on Saturdays. It's something like that. So let's be very specific about what the symptoms are. And one of the big things is has anything changed? Did anything change that could cause this problem? If so, let's look very closely at that change. And if we have lots of things going on the network, we've got multiple problems, it's typically better to deal with those one at a time, deal with those individually so we don't get our symptoms and causes confused. Step 2 of the troubleshooting methodology is to establish a theory of a probable cause. First of all, we question the obvious, like, is it plugged in? Are things connected at layer 1, in other words? We might consider multiple approaches to doing our troubleshooting or to establish a theory. We might use the OSI model as a reference. We could say we're going to start at the application layer, work our way down. Or we could say that we're going to start at the physical layer. We're going to check the cabling, and from there, we'll work our way up. Personally, I'm a fan of starting in the middle. It's called the divide and conquer approach. For example, I could do a ping, which is an ICMP message that lives at layer 3. And if my ping works, I know that I'm good at layers 1, 2, and 3, and I need to focus my troubleshooting efforts on the 4 upper layers. If the ping doesn't work, that's also good news, because I know that something's wrong at layer 1, 2, or 3, and I can focus my troubleshooting efforts there. Step number 3 is, once we come up with this theoretical cause, let's come up with a test to see if we're correct about that cause. Then let's establish a plan of action to resolve the problem and identify any potential effects. If I reboot the router, for example, today, right now, is that going to interrupt the workflow for somebody else? We need to examine that. Then, once we've determined an appropriate time to implement the solution, we might need to go ahead and implement it on our own, or if we don't have access to do whatever it is that needs to be done, we might need to escalate that problem to another group within our company. Step number 6 is to make sure that everything's good now. Is everything functional after we apply this fix that we've tested and determined to be the underlying issue? And if everything is good, great. What we can do then is document exactly what we found. So if a similar issue happens in the future or something else happens in the future and we want to look back at our service records, we've got documentation of that. So here's a summary of that 7-step troubleshooting methodology that we need to memorize for the CompTIA Network Plus exam. And I promised you at the end of this summary video to give you a big discount on the Network Plus complete video course that I did for Pearson IT certification. Here's the URL that you can go to. You can go to netpluscourse.kevin.live. Notice it's not .com, it's .live. Go to netpluscourse.kevin.live. That's just a shortcut to redirect you over to the right page on the Pearson IT certification website. And you can use a discount code of Wallace50, and that's going to save you 50% on the purchase price. So again, netpluscourse.kevin.live. Enter discount code Wallace50 during checkout, and you'll save 50% on this complete video course that talks about every single topic on the CompTIA Network Plus exam blueprint. And on that note, we're going to go ahead and wrap up this module of your Cisco Cert Success Path, where we've talked about phase 1, which is establishing a firm foundation in Network Plus technologies. You see, one of the issues that a lot of people going into IT have is they go too far too fast. They might jump directly into CCNA route switch, which is a great certification. In fact, that's our next phase. But they might do that even if they don't have any experience and they don't know some of the fundamentals that are taught at the Network Plus level. That's why I think, especially now, it's critical to learn Network Plus and go ahead and get your Network Plus certification. I'll see you back in our next module where we'll move on to phase 2, which is getting our Cisco CCNA route switch certification.